Okay, I guess we can start. I'll try to grade the exam between tomorrow and Thursday. At least I should have the first part graded by tomorrow, and Thursday the latest. I'll grade the second part. Um, Hopefully, I think. Well, I didn't get any email, so seems like no one had any issues at least taking it, which is good. Um, mm, Let me share the iPad. Uh, Okay, so just to remind you, well, maybe if there are any questions before we start, so just to remind you what we were doing on Thursday, because you were probably focused on exam stuff. So if you have like a function, right, and if you think of its graph as some sort of curve, you can think of it as some sort of roller coaster. That the roller coaster will have max and min in terms of its height. Oh, just give me a second, please. I'm so sorry. Sorry, let me just reply to something very quick. Okay, sorry. Oh, by the way, I forgot before totally forgot to mention it. Today we'll have a slightly shorter class because we do have to do run some errands that I couldn't do earlier later time. So like we'll finish probably like in an hour or so. But I mean, shouldn't be too bad. But yeah, so today usually we do like the coffee breaks or whatever breaks. When But probably today I'll just like do like a more regular like 60 minutes, 70 minutes lecture, and then um and then yeah we'll finish. But just to giving you a heads up. Um, so so what I was saying is that if you think of the function as some sort of roller coaster, then it has max and min, right? Uh, the max and the min happen to occur, at least in this picture, like where the tangent line, right, was completely horizontal, if you look at them, and being completely horizontal meant that the slope was zero. But if you think of the slope as the first derivative, that means that the first derivative has to be zero. That's why we defined these critical points as the points where the first derivative is zero. Okay. Another possibility was that the first derivative could not exist, like in the graph of absolute value, because if you remember the absolute value, there is a mean here, but the first derivative is undefined. So that's why the definition of critical point also allows for the possibility of the first derivative being undefined. Um, the thing is like, so then the other thing that we did last time was I used the first derivative test to kind of distinguish between the critical points have like a criteria that will tell you when a critical point was a max or when a critical point would be a mean. Okay, so what we're going to do today is something related to this called the second derivative test, which will give us another way to kind of identify a critical point as a max or a min. And it's in many ways it's somewhat more convenient than the one this first derivative test that we did last time. Okay, so today what we're going to talk about is the second derivative test. So let me give you which lecture is this one. Let me check the announcements. So today would be lecture 15. So we are going to talk about the second derivative test. Okay, so first, just a quick review about parabolas. Uh, so what do I mean by parabolas? What is something like a parabola? Like the classical parabola, that the one that probably everyone would remember is something like y equals x squared, right? Which would look like this. Then you could have something like y equals like, let's say, minus 2x squared plus 1. So how would that look? Let's start to think about it. What would the graph for this one look? Well, notice that when x equals 0, right, y equals 1, right? So here's 1. And then how should I draw this? Going this way or going that way? Which of the two options? First or second option? Yeah, it should be the second option. I mean, it's kind of easy to tell in the sense like, now because there's a minus sign in front of the x squared, once x gets big, sufficiently big, the values for y have to become negative. So, oops, for x large, y should be negative, so it has to be, going in the negative y direction. Okay. Now, do you like, I'm not sure sometimes what you had seen before, but these are called concave up, a concave up parabola. And this is called a concave down parabola. Does that look familiar? This concave up, concave down. I'm about to give you a definition, but just to make sure. So just maybe to go on GeoGebra. First, where do I have this? Did I delete it? Yeah, I did. It's better to like do some animations to see what we're talking about. So I can introduce two sliders. I'm going to call one A, and I'm going to call the other one B. Okay, and I'm going to have a parabola which is going to be ax squared plus b. Okay, so for example, this is showing me the graph of x squared plus 1. So again, b is a term that we're putting here. If you remember how I defined it. So notice that when I switch b, right? So what's happening when I change the value for b? I'm just shifting, translating vertically the parabola. Is that making sense? Hopefully, also pay attention to the formula here so that's to notice what's being changed, right? But as I change b, right, as I change the second number, it doesn't affect whether the parabola, if you don't want to call it concave up and down, you can call it happy or sad, right? So the parabola here is happy, right? And the mood of the parabola is not changing when you vary this coefficient. Is that making sense? So here, all these parabolas are happy, right? And but the technical term for that is concave up. Okay. Is that making sense? So, but then what happens if I change the value for a? That's just the coefficient multiplying x squared, right? So if I keep positive numbers, right? These faces are all happy. They're just like, happier or somewhat happy or not. But I mean, they're still kind of happy. But once I change the value for a, right? Once I make it 0, it's kind of like the parabola actually becomes a line, and it is like, you know, it is serious. But then once I change it to negative values for a, right? What happens with the mood? It becomes sad. Right, so what I'm trying to say is that whether a parabola is up or down or happy and sad only depends on the coefficient that's multiplying the x squared. Is that making sense? Okay, so let me write that down. So if you have like a parabola, like y equals ax squared plus b, right? These are called concave up. What's the first called? Okay, they're called concave up when a is positive, and they look literally like a smiley face. So they look something like this. And they're called concave down. Sad when a is negative. And they will look something like this. Okay, so if you thought about this one, if you think about this parabola, it looks like what? This one has a mean, right? It looks like that there's like a mean here. And if you look at the concave down, it looks like it has a max, right? And that is correct. So the concave up parabola has a mean, right? And this one has a max. Is that making sense? Any questions about it up to this point? Okay, and now why am I telling you this? Because what I'm going to explain today is that actually there's another thing, an interesting thing that happens, that the graph of any function in a sense can be approximated by some sort of parabola. Okay, so once we get into more details of what that means, you'll see that understanding what happens with parabolas is actually important, because then you would approximate the graph of a function by the shape of a parabola. And that would allow you to locate the max or the mean. Okay. So before doing that, so I wanted to talk first about parabolas so that we were all on the same page about what we need about parabolas. The other thing I had to tell you about is the second derivative of a function, which I have never mentioned up to this point. Right, so let me tell you what that is. I mean, the easiest thing is to just like do some examples. Um, so if you think about f of x like x cubed plus x, right? What would be the first derivative? The first derivative of this function would be 3x squared plus 1, right? Now, the thing is, like, you know, you can think of 3x squared plus 1 as a function on its own right. Right? If you look at this expression, like, it depends on x. So you can still take the derivative of that, right? And so you're taking the derivative of the first derivative, and just what would be the derivative of this? It would just give you 6x. Is that making sense? So that kind of looks a little bit odd. I mean, weird to write it this way, like f prime prime outside. So the way in which this is typically written is f double prime. Okay, but what I'm trying to say is that the second derivative is just the first derivative of the first derivative, which sounds a little bit weird, but and that's like the idea. So the second derivative of f of x in words, if you want to write it in words, is that first derivative of the first derivative. Or f prime of x prime. Is that making sense? Any questions about this up to this point? I'm not sure if this is confusing or not, so let me stop first here to see if there are any questions. So it is just finding the derivative. Finding the second derivative is like finding the derivative, but not of the original function, instead of like the first derivative of that function. So just to give you another example, and I'll use it in the other notations so that we start getting used to both notations for the second derivative. Let's say I gave you another function that's called g of x. Well, just to do something simple, like sine of x plus, x squared. Okay. So what is the first derivative of g of x? Well, the derivative of sine is cosine, right? And the derivative of 2x of x squared is 2x. So that would be the first derivative of g of x. And then we need to take the derivative of that again. That's the way which you would find the second derivative. So again, that's not quite how we would write it in general, but this just means take the first derivative with respect to x of what we just found. So that would give you minus sine of x plus 2. It looks a little bit odd to write it this way, But if you think about it, like, the d is kind of appearing twice. So as a symbol, what you write is d squared of g and then the x squared. So typically this is a notation. So this is like the typical notation for the second derivative in this other way of writing the derivatives. So this means the second derivative with respect to x. So in this notation, like in the previous notation, the number of primes is telling you that you're taking two derivatives. In this notation, the 2 here is the one that's telling you that you're taking two derivatives. You also put like a 2 here because of the conventions. So the 2's, like they kind of always match. So the 2 here always goes with the 2 here, and that's just telling you you're taking two derivatives of the function g. And the 2 primes also tells you you're taking two derivatives of the function f. Is that making sense? Questions about it up to this point? Okay, now here's the thing. Anyone can find the second derivative, right? It's just that like just because you can find it, that doesn't mean it's useful, right? So the next question that you have to ask is why would you find it, right? So why try to compute the second derivative, right? So what I'm trying to say is what's the point? What information does that give you? Or why is the second derivative important? Let me write it that way. Okay. And one way to think about it is that it just helps in approximating the function better. Okay. So it is useful for approximate to give a more accurate approximation of the function. So okay, so uh, okay, so oops, what do I mean by that? So we saw that the first derivative can be used to find the equation of the tangent line, right? Useful to find the tangent line. So what was like the equation of the tangent line? This can get confusing if I don't do it the right way. So if you have the graph of the function here, right? Let's say you have a point A, right? So the tangent line, the equation of the tangent line, what was the equation of the tangent line? It was y minus f of A, right? equals the slope. What is the slope? F prime of A times x minus A. Is that making sense? Or if you prefer, you can write it as y equals f of A plus f prime of A times x minus A. Is that okay? And any questions about up to this point? So that's how we found the equation of the tangent line, right? So what's the point of finding the tangent line? The idea of finding the tangent line, right, is that if you were to zoom in close enough, the difference between the graph of the function and the actual function kind of, they become closer, more similar to one another, right? So the idea of like the tangent line is that that's if you remember, like I believe there was a problem about this on the second yesterday's midterm, right, where I asked you to approximate a value. Like that can be used to approximate values of the function, because then you just approximate the value of the function with the value for the tangent line that you would get from the tangent line. But pictorially, in terms of the graph, what this is doing is telling you that you can approximate the function, like the graph of the function with the line, at least if you look close enough, okay? But you could ask, why do you want to approximate it with the line, right? Maybe you could try to approximate the graph of the function with something more complicated. Okay. Oops, sorry. I don't know why it's happening now. Oh, give me a second. Yeah. So now what I'm trying to say is that we can approximate the graph with something better than a line, and that would be a parabola. And that's what I'm going to show you now. So what is, it's called the Taylor approximation, or the, you could call it like the parabola approximation. Of second order. Or you can also call it the parabola approximation. Okay, and it's basically that, but now instead of like a, here we're going to have A and f of A. Oops. I prefer the graph from last time. So what I'm trying to say is that now we're trying to find like a parabola that approximates the graph here. Okay. So this is like a parabola approximation, the green curve that you see here. And the equation of this green curve is kind of funny. It starts like the same as before. Plus, okay, I need more space to write it. Uh, Plus, so it starts the same as before, but now you just add something that depends on the second derivative. Okay. And that's how it looks. Okay, so let's try to make this, any questions up to this point? I'm about to do an example so that you see how this looks like. So that you can compare it. Let's see, which one would be good? Um, okay, let's do it with natural log. Just give me like 2 minutes. I'll be right back. Sorry about that. So, let's say I give you, to make this more concrete, let's say I give you f of x is going to be natural log of x. Okay, and so the question is going to be find the tangent line and the parabola approximation to this function at the point a equals 1. Okay, so for that we need we are just going to use these two formulas, but for that we need the formulas for the first and second derivatives. So f of x equals the natural log of x. So what's the first derivative of x? Anyone remembers? It's 1 over x, good, which is x to the negative 1. That's useful, convenient to write it that way to find the second derivative. So what's the second derivative of x? What's the first second derivative? It just means take the derivative of this. So what's the derivative of this? Good, it's minus 1. Yes, minus x to the negative 2, which you can write as minus 1 over x squared. Perfect. Is that okay with everyone? So what's the tangent line approximation? The tangent line, right? In fact, let me draw. We kind of know more or less how the natural log looks like, right? So this is how natural log looks like. And we have this point, which is a equals 1. So here's a equals 1. We're trying to find the tangent line. The tangent line, the equation of the tangent line was y equals f of a plus f prime of a times x minus a, right? So the equation of the tangent line would be y equals, because a is 1, is f of 1 plus f prime of 1 times x minus 1. Okay, but what is f of 1? That would be ln of 1 plus what is f prime of 1? 1 over 1, right? Times x minus 1. So the equation of the tangent line, what is ln of 1? That's 0, right? And 1 over 1 is 1, so you get x minus 1. Is that making sense? So what I'm trying to say is that the equation of the tangent line to natural log at this point is y equals, oops, y equals x minus 1. Is that okay? So far, so good? But now, what's the approximation of the parabola, of the tangent parabola? That's not, by the way, no one calls it that, but you could call it tangent parabola. The approximation of the tangent parabola is this one that I wrote before. So this is for the tangent line. And for the tangent parabola, it would be y equals f of a plus f prime of a times x minus a plus 1/2 f double prime of a. Oops, let me write it. It would be y equals f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared. Okay. So if you notice, this is exactly the equation of the tangent line. So it always starts with the equation of the tangent line. You just basically add some extra piece. So the equation of the tangent parabola is x minus 1 plus 1/2. What's f prime of a? Well, it would be minus 1 over 1 squared because a equals 1, right? Times x minus 1 squared. Is that making sense? Questions about this? Of how I'm plugging things here? So this is the equation of the parabola. Well, in fact, I'm going to put them on GeoGebra because it's way easier to look at all of them three together. Okay, but it's kind of fun to do. So let's go back to GeoGebra. I'll give you a second to write it in a moment. So this is the equation of the natural log, right? We're looking at the point 1 comma 0. That's where we're approximating everything. So let me make this bigger. Okay, and then the equation of the tangent line was y equals x minus 1. So you see, it does look like the tangent line. That's good. And the equation of the tangent parabola, which again no one calls that way, or the approximating parabola, it's called the second order Taylor approximation if you actually want to use a proper terminology. But once you take that calc 2, you'll do that with a lot more details. So I'm just giving you what you need for now. It was y equals x minus 1 minus 1/2. 1/2 is 0.5, so x minus 1 squared. And that's the green one. So that's the equation of the parabola, which is in green. Let me on my formulas. Is that making? Do you see it? Do you see the green one? So it does look a lot better. I mean, hopefully it does look like a better approximation to the curve. Again, the curve we care about is the blue curve. Maybe I should thicken it. And it does seem. I mean, once you get very close, there's almost no difference between the pink and the green, right? If you're like in this region, you can almost not tell them apart. But once you start moving a little bit away, kind of it looks like the green one tries to remain closer to the blue curve for a while. Is that making sense? So it kind of seems like the green one follows more closely to the blue curve, if you know what I mean. Is that plausible? So there's like a region where they're almost indistinguishable, but if you zoom out, kind of like if you zoom out a tiny more, a tiny bit more, the green curve kind of resembles the blue curve for longer periods of time, if you want to think about it that way. Is that making sense? So I'm just trying to say that no one ever said that the only way to approximate a curve was using a line. If you want to approximate a curve with a parabola, you can, and I just gave you the formula for doing that. Any questions about this? So far, so good. So now what does the second derivative test say? Now, okay, now at least it kind of makes a little bit more sense of what's the point of the second derivative. The second derivative is kind of what helps you find this parabola that approximates the curve. So without the second derivative, you would not be able to approximate the curve with the parabola. So it comes as an approximation. It helps, it is introduced to approximate the curve better, or the function. But what does the second derivative test say? Well, the idea is that imagine that you had, again, the graph of the function. So we suspect that there's like a mean here. Maybe there's like a mean somewhere in here. So let me take that to be A. So A for now is going to be like a place where which is a critical point. So what does it mean for A to be a critical point? It means that f prime of A equals 0. Okay. And now what I'm going to do is find what's the parabola approximation to the curve near A. Well, if you remember, like the parabola approximation is that y equals f of A plus f prime of A times x minus A plus 1/2 f double prime of A times x minus A squared. Is that making sense? Now, I don't know what f of A is. I don't know the value of the function at A. Like, just some number, right? But I do know, I can say what this is, right? What should this be? Any guesses? It should be 0. Why? Because we're assuming that A is a critical point, right? So this should be 0 since A is a critical point. And then we don't know what the second derivative is, so let me put it like this. F prime of the F double prime of A okay. Is that making sense? So the equation of the approximating parabola here is just y equals f of A plus f double prime of A over 2x minus A squared. Is that okay? And what do you remember? Okay, and now this makes sense. Why did we go over this review of parabolas? Because this looks very similar to the parabolas, the formulas for the parabolas that I wrote before, right? So how does the parabola look here? Happy or sad? Yeah, I should be happy. The technical word for it is concave up again. And in the concave up case, what's the coefficient that's multiplying the thing with x squared? What was the property about that coefficient? The property about that coefficient in the concave up case, the property about that coefficient is that it had to be a positive number. Okay, so for this to be like look like actually like how it looks like for it to be like a min, that requires the second derivative to be positive. So if the second derivative of a is positive, then the approximated parabola is concave up or happy. Is concave up or happy. And so f of a, so the function must have a relative mean at a. Is that making sense? Is that okay? And what do you think would happen in the case for a max? So what should happen in the case of a max? In the case of a max, it should be concave down, right? So it had to be a sad parabola. Sad parabola would mean that the coefficient in front of x squared or x minus a squared would be negative. So this coefficient has to be negative, and that can only happen when the second derivative is negative. So if f double prime of a is negative, then the approximating parabola is concave down. Sad, and the function has a relative max at a. So let me put this in with some colors to distinguish them. Oops, let me just underline it maybe. So what the second, and that's basically what the second derivative test is. It just tells you that if you want to know if something is a max or a min, you just look at the second derivative at that point and for a critical point, and then like the sign of the second derivative tells you whether you get a max or a min. So it doesn't require you to analyze how the whether the first derivative changes from positive to negative or backwards. Is that okay? And you'll see it's a very useful way to check for max or min. It's like it's a lot in many ways it's very fast. It's a lot faster compared to the previous method. Okay, so let me just let me give you an example that we had done before, and now we're going to use it with this criteria. So if we go back to the lecture from, okay, let's do again x cubed minus 3x because we had analyzed it before. So that would be the first derivative, right? Um, which and the second derivative, what would it be? It would just be 6x. So if you remember, what were the critical points for this function? The critical points were at a equals 1 and -1, right? Because it would be when f prime of x equals 0. So that's just 3x squared minus 3 equals 0, which is x squared equals 1, x equals plus or minus 1. So if you remember, there were two critical points that we had found. So what's the second derivative at 1? It's just 6 times 1, which is 6. That's positive, right? So if it's positive, it's a concave up, right? It's positive emoji. You're feeling happy. A good way to memorize this is to make a face. So the eyes of the face is the sign of the second derivative. So in this case, the second derivative is positive. So you make a face where the eyes are positive, and so that means that you have to be happy. And if you look at it, what does that mean? That means that there was a mean, right? And is that making sense? So now the second derivative is negative and -1. So you make a face where the eyes are negative. So that means that you're sad. And so that's a max, right? And -1, sorry. Is that okay? And that's, if you go back to the notes from last time, that's exactly what we had found last time regarding what was a max and what was a mean. We had found that 1 gave you a mean and the -1 gave you a max. Are there any questions about this? Uh, okay, so as I said, today I did have to end the class earlier. So this is a good place to end. My next time tomorrow, what I'll do is like restart this again with the second derivative test, do more examples, and we'll see how to use this for some applied optimization problems. So that's the next goal here, to do some applied optimization problems. But yeah, yeah, let's just finish here for today at least, and then tomorrow we'll have like full lesson, full class. And again, I'll try to have the exams graded by tomorrow or Thursday, the latest. Okay, good. I'll see you tomorrow then. See you tomorrow. Bye.